the sessions are planned in such a way. And in some general instructions regarding attendance, a lot of you guys have asked about. In total, in all 3 sessions combined, we will be giving 10 attendance sheets. And in this session, today's session, we'll be giving 3 attendance sheets at various time points. So you need to fill it up. And it will be open only for 5 to 6 minutes. So beware about those things. There are people in both YouTube as well as Microsoft Team chats. They will be giving you instructions, or if you have any doubts, you can always ask them. Even sometimes if you have if it is a very hard topic and a lot of people are asking it, even I will be ready to reteach it again. So feel free to ask doubts. There are people in both YouTube and Microsoft Team chats who can ask doubts, or if it is, once again, if it is any hard topic, I will be reteaching it again. So don't worry to ask doubts. And once again, attendance sheet will be given at any point of time. You should be aware of noticing it. And that's all. First, without any further delay, let's start off with the session. I hope everything is clear. Let's start. First, let me give you a roadmap of what we are planned to do in this session, in all 3 sessions. Just first, in this session, we will be dealing with something called as root finding. If you have never heard of that term, don't worry, we will go from basics only. First, root finding. After that, something called as differential equation. Right, we would have learned what differential equations are, but we'll give you another perspective about how these things are covered up. Next, introduction to numerical methods and Octave. Once again, it is MathLab and computational tools. We are going to see how math can be implemented in some code. MathLab is what we aspire to have, but Octave is what we are doing it now, right? Because both MathLab and Octave have same code, you can do it in anything. Next thing is, third one is Fourier series, which is really an important topic in your college things. So, and we will be analyzing some noise in signal, and also finally we will be coding everything in Octave. So we will be going from very basics to whatever level we have aspired to do. All right. So let's just start with the session. This session, what we will be doing, learning outcomes of this session is simple. Most important thing, root finding techniques. Next is iterative methods. You will be learning, just a name say. We'll be explaining it everything. If you don't know, just don't worry, we'll be explaining it. And then you will be getting introduced to something called as differential equation. After it, you will be understanding what numerical theory is, how it is different from how mathematics have been taught in our school, right? And then using 2 root finding techniques. There are a lot of root finding techniques, but we'll be covering it 2 in the session, right? And then how to solve D in analytical things. First, you will be introducing to differential equation, and then obviously you will be solving it, right? And then you will be given the motivation for numerical methods. So that's all the learning outcome of this. We will be dealing with in particular at every single point, right? Let's go to the session. First, polynomials. Let's start from the basics. Why polynomials was invented? As there's a saying, necessity is the mother of invention. They needed something, so only they invented some topics in both in mathematics as well as in science or any genre. So what mathematicians thought was, they wanted to analytically do whatever they observe. Like, let's say rain is showering, or a ball is falling from top. They needed to observe all those phenomena and write on paper in analytical thing. Like, if we are observing something, but we need to write it in mathematical terms and get some result. That's what the prime motto of mathematicians are. And of course, geometry is one of the things which is given in like geometric positions, shapes and stuff like that. But analytical, given some variables, they are supposed to model something, how it behaves, the behavior of something. They thought of modeling it. Modeling is maybe a bit high level term, but okay, let's say they just want to transform whatever they observe into a paper with equations. That's what the prime motto of mathematicians was back in some 200 years back, right? Or a lot of years back. Let's see. This was the motto. And to analyze it, what they thought was, they created something called as polynomials. Let's see. First, there are 2 terms in polynomials. This is simple things, but still they will revise it. dependent variables and independent variables. Independent variables means it's just any variable that you manipulate. Some things we can change to see the output. You know, in simple terms, if you want to say independent variables are input, dependent variables are output. Imagine some scenario. Let's say a ball is falling. You can say, you can vary the time. At time at which I measure the height. Height I can't change, but the time where I measure it, I can change, right? So time is the independent variable. Independent variable is what you are trying to give as input, and dependent variable is something which you are getting as output. All right. So in simple definition, once again, always keep in mind the prime motto. We need to model everything. So we are having an independent variable. Maybe we can have independent variables, but in this session we'll be covering only one dimension. So we are having an independent variable and we are giving it and we for a phenomenon and we are getting the output. Prime simple example is a ball is falling. I'm giving time as an input. Time as an input in the sense where the time when I measure the height, and the height I measure I cannot manipulate. I cannot say okay 2 meters is there. What's the time? No, time we are measuring, time we are giving the input, and height we are observing, right? So dependent variable is the output we are aspiring to get, and independent variable is what we give as input. All right. So simple examples, let's say it just y equal to x square and y, this is simple polynomials. Polynomials is some x bar n terms. With the degree n means there is an x bar n coefficient term is that, and then it will be of some of some x terms, right? So that's all polynomial is. The reason for revisiting is because we are going to solve it. Now, once again, the thing is mathematicians wanted to model whatever they observe into a function, right? As I said. So they created polynomials and used it to explain the model. Classic example is this one. If you see this ball, it is just moving on. And if you want to find this height, I think you would have studied in the laws of motion that h is ut plus half at squared. So they found that this is a polynomial. So we can find a, we can find u, and then we measure the height. Here, u and a are parameters. Parameters is in some sense, there are some constants. All right. T is an independent variable and h is a dependent variable. So I hope you would have understood why polynomial was created. They wanted to model something into paper. On paper, they have to form some equations and analyze what is happening. Okay, so let's just go to the next screen. So after they found this polynomial things to model something, the first thing they thought was, why not we solve them? Right? Okay, you can say, oh, this is for this equation, this h equal to ut plus half at square. We can say, oh, that equation is there, no sir, like minus b plus or minus square root of b square minus 4ac. Okay, for quadratic, right? Okay, so what about cubic? Well, cubic also there is an equation, but it's very big. Like, what about degree of 5? What about polynomial of degree 7 or 100? Because polynomial can have degree of any natural number. So then mathematicians thought. So these methods are something which is restricted. That minus b plus or minus square root of b square minus 4ac by 2a, that formula is only restricted to quadratic. We can't do anything. And for cubic, there is one formula, but we don't care. There is some formula. But what they thought was they needed some general method. Given any polynomial, I should be able to find an equation, find a solution. Right. So solving it's nothing but dependent variable equal to 0, which means some basically for this, make it equal to 0 or some constant, and you will end up in an equation. We need to solve it because getting a polynomial is simple, but why the most important thing is you need to solve it. You need to find some critical values in the sense some useful info you have to extract from it, right? So for that you need to solve it. And what mathematicians thought was they needed a general method. They don't want to find every single formula. Okay, for biquadratic, for power 4, create a formula. For power 5, create a formula. No, they wanted something more generalized. All right. So they were in motto of finding. That's what first thing is Newton-Raphson method. So before going into what Newton-Raphson method is, we need some prerequisites. Let's just go over it. First, recap about derivatives. I know you guys would have learned about what derivatives is. Just, I think you know the rules of derivatives, how you can differentiate sin x function or any polynomial function with n x bar n minus 1, stuff like that. Now let's shift from that without just substituting values and differentiating, let's see what it really is in terms of coordinate geometry. What dy by dx is just slope of a tangent at a point x comma y. Let's give you an example. So let's take a general function y equal to x square, and you know the differentiation of this nothing but 2x. So what I've done is, if you want to know it, it's just simple. Just focus on this equation. I hope you can see my cursor. This is y minus n square equal to 2n into x minus n. Is it ringing a bell? It is nothing but a slope point form. I hope you would have known this slope point form. Y minus y1 equal to m into x minus x1. So what I've done is I've taken n comma n square as a point. X1 is n, y1 is n square. So n comma n square is a point, and the slope is 2n. All right. So the slope is 2n. So I've done y minus y1 equal to m into x minus n. This 2n is obtained from this derivative. Y dash of x is 2x, right? So let's see what it is then. You see this graph. See, I've done the same thing here. If you can see, this is y minus y square equal to 2 into x minus x1. See what happens. At every single point, it serves as a tangent. You know what tangent is? Tangent is a line that meets the curve exactly at one point. It meets the point exactly at this, and the slope becomes f dash of x. I mean, it's simple, but if you guys don't know it, just know it from now. The derivative of a curve is nothing but gives the slope of the tangent at every single point. All right, so this is some visual example of this. You can see I'm varying n, but in every single point it serves as a tangent. All right, so now let's go to the next prerequisite. Okay, as you would have seen, first we have in Newton-Raphson method. Once again, the motto is we are going to learn Newton-Raphson method. The reason is we have to solve a polynomial in a more general way. Remember, once again, there are formulas for quadratic, biquadratic, or everything, but we need a general thing. So first prerequisite, we have completed derivative. What derivatives? An alternative perception of derivative. It serves as a slope to the function. All right. So now, something called as iterative methods. Now, iterative methods is something which we have never seen in a high school or something. So what iterative methods is? It's just a condition given to the formation of a sequence. You know what sequence is, right? Like you would have learned what arithmetic progression is, what geometric progression is. But that is based on some starting term and a ratio, or starting term and difference. But here, an iteration is you have given a condition for the next term based on the current term. Listen properly, the condition based on the current term to give the next term. So xn plus 1 equal to, let's say, root of 2 plus xn. This is what an iteration definition is. If I say xn plus 1 equal to root of 2 plus xn, with, of course, x1 is needed because you need a starting point to iterate. So x1 equal to 1, what will it do? So x of 2 will be root of 2 plus 1. So x2 will be root 3. X of 3 will be root of 2 plus x2. What is x2? It is root 3. So root of 2 plus root 3, which is root of 2 plus. So this is what an iterative methods is. This is one of the key concepts which has never been taught in school, but it is always useful in something called as numerical methods. So let's say, of course, there are two types of iteration. We are actually don't need to know this, but I'm just giving it. The converging iteration means this sequence, right? Root 3, root of 2 plus root 3. The next term will be root of 2 plus root 3. It will go on like that, right? So that is converging to a number. If you want to see graphically, see this point. I think you can see this. I've started with x1 equal to 1. Yeah. I've started with x1 equal to 1. So this is what converging iteration is. Next, let's go to this diverging iteration. Diverging iteration means it diverges to some different value. Let's say xn plus 1 equal to sine of xn. Okay, this is also a condition, right? You're giving a value, take a sine of it, and then observe it. So xn plus 1 equal to sine of xn will give you x1 equal to 1, and x2 will be sine of 1. All right. Because just substitute, x of 2 will be sine of x1, which is 1. So sine 1. x3 will be sine of x2. So x2 is sine 1, which is, of course, a value. You're substituting it and getting the value of x3. If you want to see this graphically, see this. It is sine x. I have iteration starting from 1, right? See this point. I'm giving it the cursor. See this? You will be understanding how it varies. So this is first iteration, it is 1. After it becomes sine of 1, which is 0.84, right? And then it is 0.83, 63, 59, 55, 53, 5.5, and then 0.48, 0.46, 0.45, 0.43. It goes on like this. So this is what an iteration is. The reason of giving you this is just know there is something called as iterative methods, and you will be given a condition and an initial value. From there, you will be finding next values. So why are we learning it? Once again, you are going to find what Newton-Raphson method is, and which is to solve any polynomial in a more general way. So finally, after learning what derivatives is, what iterative methods is, let's go to Newton-Raphson method. Fine. As I said, Newton-Raphson method is also something called as iterative method. Iterative method is, you will be given a condition with the initial value, you will be go on proceed. So the condition is here. Xn plus 1 is nothing but xn minus f of x by f dash of x. F of xn by f dash of xn. So if given x1 equal to xn equal to something, let's say I'm given a value, you will be substituting here, you will be substituting in f of x, you will be substituting in f dash of x, and where f of x is the function you need to solve, which means for any polynomial of any degree, even may it be the degree with 100, you can still solve it, right? That's what the power of Newton-Raphson is. And of course, you can ask, in all previous iterations, I've given x1 equal to something, but here I haven't given him, what about x1? We can choose any arbitrary value and still we'll end up having a solution. Well, it may look false, but let's see. Once again, if you ask why is this formula achieved, a picture is worth 1,000 words. So let us explain in detail with a diagram. So listen carefully. If you have any doubts, you can ask chat mods or you can ask me to repeat it, but let me go by step. First, I've taken a function x1 equal to f equal to x square minus 4. We need to solve it. Basically, we need to obtain a solution where x square minus 4 equal to 0. It may look simple. You can simply analytically solve it, but let's see how this Newton-Raphson method corresponds to a solution. So this is what the equation is, right? Xn plus 1 will be xn minus this f of xn divided by f dash of xn. If you want to know, this is xn square minus 4 divided by 2 into xn. All right. So I didn't do anything. I just substituted f of x equal to x square minus 4. And of course, derivatives, f dash of x is nothing but 2x. Constant is 0. The derivative of constant is 0. So f dash of x is 2x. So substituting xn is 2xn. So basically, I need to solve it. Right. What this formula does, let's see. First, you have to draw a tangent line to this point. What point is x1 equal to 1 I have taken. So what would be the point? 1 square minus 4, which is minus 3. So this 1, this is minus 3. I hope you can see it. So this is a point which I have taken as initial. We should end up getting this point, 2, 0 or minus 2, 0, whatever. Basically, we need to get a solution. So first, what you need to do is draw a tangent line to this point. So, this derivative term, right? What it does is drawing a tangent, I said. That's what the correlation between this Newton-Raphson and this derivative. So if you have drawn a tangent line, first you need to draw a tangent line and find where it meets the x-axis. This is what x-axis is, and this tangent, of course, it's a line. So it will have an x-intercept. You just need to find that point of x-intercept, where it meets the x-intercept. So this is where it meets for this curve. For this x square minus 4, this tangent line meets the curve at this point. All right, for x1 equal to 1. Now let's see. What you have to do is, you have to take a vertical line to this point. Basically, you have to find f of x values for the point where it has touched the x-axis. So this part, our point is, we can see it's 2.5. And from here, you are drawing basically a vertical line to the curve. And this is what becomes our second point. Can you understand? So our iterative, this condition, all right, what it does is, you're drawing a tangent line meeting the x-axis at some point, this 2.5, and drawing a vertical line to the curve where we intend to find in the solution of. So this is what our second point is. So see, the condition is simple. Iterative method always gives you a condition and you have to satisfy it to proceed to the next point. As we have seen, this is what an iterative method is. So for in Newton-Raphson method in particular, you have to draw a tangent to and make it meet the x-axis at a point and draw a vertical line to the curve where you intend to find the solution. So this is what general is. If you substitute here, you will get 1 minus x1 square minus 4 is 1 square minus 4, 1 minus minus 3 by 2, 1 plus 0.5, 1.5, which is 2.5. Still, we ended up getting the solution. All right. So this is what second point is. Now, should we stop here? No. What iterative method is doing? Keep on repeating it unless you converge to some point or diverge to some point, whatever. Now let's move on to next. Once again, this is x2. As this is so narrow, I just zoomed out here. So this is what x2 is. I've drawn a tangent line. All right. And it met x-axis some point over here. I hope you can see it. It's so narrow that it's so close to 2. You can see it. I mean, I don't ask you to say that, okay, we achieved the solution. I'm saying it's so close to 2. Basically, initially we started off with 1. We went to 2.5, which is closer to 2 than 1. And then now we went to a point where it's so close to 2. So basically this tangent line meets at this point, and we are drawing a vertical line here, and that becomes our x3, right? So, well, I mean, once again, let us give you a visual so that you can understand it properly. This is our point. Once again, f of x equal to x square is the function which we intend to solve. All right, and I'm taking x1 to be 4. Simply arbitrary. I can take whatever point I wish. So here I'm taking x1 equal to 4. Now, let's see what happens. Once again, this is some GeoGebra code. I don't need you to know it and all. Just see. I've say this is what iteration number is. This is what our Newton-Raphson method. You can see, right? X minus xn square divided by f dash of xn. F of x is x square. So xn square is that. And f dash of x is 2x. So 2xn is that. And this is some iteration thing. And see, this point is what our current point is, 4, 16. Because I've taken x1 to be 4. So the function will be 16. The point is somewhere there, above. I haven't focused it. So let's say the point is there. Now, from here, we need to find the solution. And it intersects the point at where? 2, 0. If it is a lot of things to say, go slowly. We'll repeat the video twice or thrice so that you can understand it. All right. So now let's start. First, we are drawing a tangent line, and you are making this a point where it meets. It meets as 2, 0, as we can see. It's 2, 0. It's simple. And we are drawing a vertical line so that it meets x3. So this is what our next iteration is. Now, moving on. After it goes here, once again, drawing a tangent from this point, meets somewhere here, which is 1, 0. This second iteration, and the current point is 2, 4. Once again, creating an iteration. Now the point is 1, 1, and it meets the x-axis at 0.5, 0. Next, it meets at 0.25, 0. The current point is 0.5, of course, and then goes on. First, what is the solution? We know that for this x square equal to 0, x equal to 0 is a solution. Let's see what it happens. Now it goes to 0.13. The current point is 0.25. Yeah. Next, it goes to 0.06, 0. Of course, it came so close to 0. And 0.03, 0.02, 0.01. And yeah, we ended up with a solution of 0.0, 0, in the iteration of just 10. Now, let's take a breathe and analyze what happened. You would have understood what Newton-Raphson method is. Basically, you are drawing a tangent, meeting at x-axis, taking a vertical line with a curve, and it shows you to be the next point, right? So, how this becomes this function? This is basically, if you analyze what is happening, you can substitute that to be a slope point equation, and you end up getting this formula. We are not diving there, but I'm just saying if you want. So our whole point is, I think we are done with knowing what Newton-Raphson method is, how it works. See, the power of this is two things. First, it is general to any polynomial. I have taken examples of only quadratic so that you will know what solution is, and you can analyze from this graph how it works. Second thing, it doesn't matter which x1 you choose, but you will still end up getting the solution. If you want to know why is this serving as to solution, how is this tangent line subtracting it from some x value giving a solution is, that's an interesting question, something called as gradient descent. We are not covering it up. It's an amazing topic. If you want, you can research it up, but it's up to you to do. What we want you to know is there is something called as Newton-Raphson method, how it works, and whether it is working, a visual proof of it. Now, you would have asked, okay, if you don't want x1 to be x1 is to be like anything. If you want x1 to be anything, what is the significance of x1? If you have that doubt, let's just see this. Examples of different x1. And now I have taken something a bit different, x cube minus x minus 1. So this is a different graph. Other than being quadratic or something, you can see there is some solution at this point. Okay, this point. I have taken x1 to be 3, which means once again there's some code. This is what our done is x minus f of x divided by 3x squared minus 1, which is the derivative here. You can simply differentiate it, right? X cube is 3x squared minus x is minus 1. Minus 1, of course, the derivative is 0. So this is what the thing is. And this point is what our current point is. This is what the intersection point is. And this is what the number of iteration. You don't want to know this, but just analyze how this point, like there are multiple points here. To avoid confusion, I've clearly written down here. See, first it is 3,23. Analyze how it works. It goes here. And then after first iteration, it goes to 2.12, 6.35, some point. You can see it gets closer and closer to x-axis. First it was 23. Now it went to 6.35. What about next iteration? You can see here also. Well, we will replay it again if you want. Yeah, after it went to 1.52 for 1.6 value. See how drastically low is. After it went to 0.24, so close to 0. Then it went to 0.01. Yeah, that's all the limitation is. And 0.0. See, within like 5 iterations or so, it achieved the solution which means. Once again, you can ask, okay, when do we need to stop? If you ask that question, it's really a good question, because if you do analytically like this, you can say at 0 we can know it. But if you want to program it or something, there's always called as some threshold value. Let's say I'm getting first for this thing, I'm getting 1.32 as solution. Let's say I'm doing it in some program and it says first I'm getting 1.32 4444. Next stream I'm getting 1.32 4443, which means the difference is so less, which implies that I've achieved the solution. If the difference between two consecutive points are so less, if you want, we can replay it again. See, first 23 is there. After it went to 6.3. So difference is high. When the difference becomes so less, in the sense it has reached the solution. All right. So that serves as your ending point. If you want to program it, that's what the general procedure is. The difference between the first iteration and the next iteration is so less. All right. So if you had you asked that question, it's a good question, and that's what the solution reason is. Now, let's go to the other example of x1. Let's say x1 equal to 0. Well, this is a classic example. This gives you how this method serves as to be a solution. See, once again, I said this slope, that gradient, I said gradient descent is an algorithm behind this working. And the reason is this slope serves as a direction in which it nears the solution. Correct? You can see from this example, this curve is there. This tangent is getting closer and closer to it. Or classic was this one, x squared. See, the curve was like this. You are going near and near solution. This tangent serves as a direction in which you have to go. It goes less steep and steep so that you can near the solution. Correct? So in a way, you can understand that this direction of the slope serves as a direction in which x has to reduce so that it can achieve a solution. So now, why x1 equal to 0 is a classic example, you will understand. So this involves a lot of iterations. Let's see. I started with x1 equal to 0. So there is something called as minima, right? In 12th grade, I hope you would have remembered something called as this again in the extremas. Here there is a minima. Well, I think, yeah, this curve will wait. I don't have a better picture of it. Okay, there is this curve. Here, there is a minima, and you know that in extremas the slope changes the direction. So wait, I've given a clue to the assignment question itself. where like extremas are there, there is a possibility of problem with Newton-Raphson. But you will see here, there is an extrema over here. So there will be two different directions. Direction in the sense the positive and negative values I'm saying. In one direction, one side of the minima, there will be slope direction will be different. Slope magnitude will be different, and another direction, the sign will be different. All right. So this example is a classic one to show it. Once again, see here, it's 0, -1 is a point, the initial point, and it intersects here. This is the iteration, and this is the same function. I've taken x1 to be equal to 0. See how many iterations takes. First, it goes here, and it goes here, goes here. First, analyze without saying anything. Just analyze how it works. Yeah. Finally, it ended up in the solution after some 25 iterations, I guess. Yeah. Now let's replay it. What it does, there is something called as this minima. This minima, what it does is it prevents it from going here, because in this over this minima, this sign of this slope differs, because here it is in this direction. Over here it was like this, right? The angle was positive, and here it's an acute angle, and here it's an obtuse angle. That's what the whole difference is. So what it does is it just kind of prevents it from reaching the solution. And you can clearly see, first it goes here, goes here. Once again, I'm just following the Newton-Raphson method. Whatever algorithm you've learned, we are just following it, and see how many iterations it takes. Oh, it goes on here and here, and finally, yeah, after some point over here, it reaches here, the point where it needs to be a solution. Oh, sorry, yeah. Yeah, from here it goes. Okay, after it just reaches a solution peacefully. So key point, it doesn't matter whatever x1 you take, you're getting a solution at least. So most important point you observe is having an extrema in the plot and choosing an x1 close to it have a problem. I'm leaving it to you because I guess it would be one of your assignment questions. So this is what you just think about it. At minima, there some problem happens, right? And close to it, the sign of the slope differs, because here it's an acute angle, the slope is, and over here it is, yeah, here it's an obtuse angle, purely an obtuse angle. It just goes away from it, correct? So that's all for this Newton-Raphson method. Let's just summarize what Newton-Raphson method is. Given a point, take a slope to the curve, take the tangent to the curve, meet it at x-axis, draw a vertical into the curve again, and the point becomes your next iteration. From then on, you have to proceed with it, and we will end up getting it. We will end up getting a solution. So I guess that's all for Newton-Raphson method. Now your attendance sheet will be given. I'm giving a 5-minute break. Just analyze whatever you have done, fill in the attendance form. We'll be back. If you have any doubts, you can ask now. You can chat with your moderators. I can see. Yeah, someone has asked Newton-Raphson for complex root. See, the thing is, we are analyzing it graphically, right? So if it is a complex root, we wouldn't have any solution. For here itself, it's a cubic equation, and as per some complex root theorem, the highest degree of the polynomial corresponds to the number of roots, both real and complex together. But here, as per us, we have only one real root, so we'll end up having only one real number in real line. Of course, there are two complex roots we can't find, because the whole motto of Newton-Raphson serves with this graphical thing, right? So we can't find it find the roots for complex things. Of course, back in those days, we wanted a solution for this real time. There can be a complex. That's a good question. I'm let's meet it within 2 minutes. Just fill up your attendance form. It will be open only for 5 to 6 minutes. If you don't fill it now, you will lose an at least one thing on. So yeah, I guess you would have filled your attendance sheet. I think we can begin our session. Yeah, someone in the chat has told that choosing different initial points will increase the number of iterations. Yeah, you are 100% right. That is a point, and the reason is you can choose somewhere the different point here. That won't affect your number of iterations much. But the key point is the choosing point over somewhere in the near minima or maxima will, of course, affect your point. All right, so that was really a good case. Now let's go to bisection method. Once again, keep the motto behind. What we need is we need to find more general method to find a solution, and we ended up understanding, I guess, Newton-Raphson method. If you have any doubts, you can also ask them. Now let's go to second method, bisection method. Well, to persons who know what binary search is, this is somewhat similar to it. But if you don't know, don't worry, you will understand it. It's simple only. Once again, it is also iterative method, but here it's just a bit conditional iterative method. You will understand as we go on visualizing it. Once again, in this method, you will be choosing two initial points. What initial points? Of course, it doesn't matter, but you will be choosing two initial points, but with a condition on the opposite sides of x-axis. So basically, you will have a curve like this. This was some x cube minus x minus 2, I guess. Some curve. You have to choose two initial points, x1 and x2, on both two different sides of the x-axis. Basically, one should have y greater than 0, and it should have y less than 0, right? Or f of x2 greater than 0, f of x1 less than 0. So now, and this is what the condition is. I don't want you to memorize it or know it. We are here to learn what this method does. It's just how you program a computer. This is what the algorithm is, but just first know how it works. Let's go by visualization. So this is what the function is: x cube minus x square minus 2. Okay, so this have a 2 minimum and maximum. So close, similar to the previous curve, but of course there are some differences. The function value is itself different. Now I've taken x1 to be 1 and x2 equal to 2. How would I know f of x1 and f of x2 greater than or less than 0 and greater than 0 is? It's simple, like just substitute value 1 minus 1 minus 2, which is minus 2 is less than 0, 2, 8 minus 4, 4 minus 2 greater than 0, right? 2 greater than 0. So you just need to take two conditions based on this, and then first what you need to do is find x mid. X mid is nothing but midpoint between 1 comma 2. No, not technically midpoint. In the x-axis, find what is the midpoint between 1 and 2. Only in the x-axis. Once again, I always have this confusion of drawing a straight line and finding midpoint. That's completely different. Here, what you need to do is find x1 equal to 1 and x2 equal to 2. Take a midpoint of it. That's what you have to do here, right? Once again, so 1 plus 2 by 2, you are getting 1.5. So it is somewhere here. I've zoomed in here, right? So you have taken 1.1, 1.5. Similar to the previous thing, you have to draw a vertical line to the curve. Same as before. There we have computed some formula, but here you are taking some midpoint and you have drawn to the curve. All right. So this is what f of x mid. Now find in which direction of x-axis it is, whether it's upside or downside, or basically find the function value at this point. So if I find f of 1.5, basically substituting here, you will end up getting minus 0.125, which is negative, right? So what you need to do is you would have chosen 2 points. I have chosen 1 and 2, and where one is at negative y-axis direction and another one is in positive y-axis direction. I mean above the x-axis and below the x-axis. You have to replace whatever whichever x1 having in negative direction with this x mid. So basically we are neglecting the previous negative point. Let's say for a while, let's name it as this positive point because it's in above x-axis and this below x-axis. So this negative point. So we end up having a point which is less than 0. The midpoint is less than 0 basically. So what we are going to do is we are going to replace whatever the negative point which was before that with the new point of x mid. So x1 was here, which was negative, and we ended up finding x mid, which is negative. So what we need to do is we need to eliminate this x1 and replace this x1 with this new point. So basically, think like this. You are moving this x1 to this point. I have a better animation here, but for now, let's think like. So we are moving close to this x-axis. What do you mean by moving close to the x-axis? Along the curve. This is a curve, right? We are moving to the close to the x-axis along the curve, which means we are technically finding the solution. Can you imagine like that? Right? We are basically moving from here to here. Now this point remains unchanged because we are dealing with only this negative f of x values, right? So this remains unchanged. X2 is still 2 and x1 has changed from 1 to 1.5. All right. Now this is what your conditional iteration is. You have to proceed this further. Now, there is a simple question. You just need to answer it. X cube minus x square minus 2. This is what the function is, the same function. Now, check what the next iteration is. X mid. I've taken x1 to be 1.5. Yeah, because I've taken 1 and 2. Now, as f of x1 less than 0, we have replaced this x1 with this 1.5. So x1 became 1.5 and x2 is still 2. Now, proceed with this algorithm and find where this f of x mid lies. Is it above x-axis or below x-axis? I mean, in a way, you can say, should I change x1 or should I change x2? There are chat mods, I think, will be ready with the polls. You just need to tell the answer. Shoutouts for the rapid answer, I guess. Yeah, come on, people, you can tell this. It's simple, right? You have to find midpoint and just check where f of x mid is there. Yeah, someone called Vasudev Krishna and Mayank Kumar have told the answers first. Yeah, congrats, people. I'll wait for a minute or so that other people can also find, just get comfortable with this. You can just move on to the next. And then we can move on to the next thing. So technically the answer is, we can say here, if you see, this becomes our x mid. X mid is basically 1.5 plus 2 by 2, which is 3.5 by 2, which is 1.75. So x mid is lies somewhere here. So if you draw vertically into the curve, the function becomes this. So basically this is the next, this lies in the above x-axis part. So you have to replace the previous x mid thing to this. The previous x2 was positive. So I have to move this point to here. I have to replace this x2 with this x mid. So now what it becomes? X1 is 1.5 still, and x2 becomes this new x mid. What is x mid with? Some 1.75. All right. So now you can, I think you can intuitively imagine what we are doing is, from both the directions, we are moving closer to x-axis. Taking an average is one step going in doing that. We are basically going closer and closer to x-axis. So how long do you think we will repeat it? Can you guess? We will be repeating till when x1 and x2 gets close, so close. If it gets so close means basically you are at the solution, right? If I'm moving it here, like let's say I'm just moving, it's so close to x-axis, so I'll be moving it here. It just goes on moving till this 2 becomes so close, which means you are here, which is nothing but our solution. Once again, remember the motto. We are intended to solve this function equal to 0, and we are doing it. Basically, by choosing the two things we need to choose is 2 points in the opposite sides of x-axis. All right. So this is what the animation I have told about. So yeah, this technically a function, technically that function. Now I have taken 2 points, x1 equal to 1 and x2 equal to 2. This midpoint is 1.50. You can see here as well and here as well. So this midpoint is 1.50, and you can say that it is less. It is so close to this one. It's so close to x-axis, but it is on the negative part of x-axis. Also, there is also a case. Sometimes, accidentally or unaccidentally, the midpoint becomes your solution. What if I haven't mentioned it, but it's obvious. I've said when in this condition, I've said if f of x is less greater than 0, put x1 equal to x2 equal to mid. Else put x2 x1 equal to x mid. What if f of x becomes 0? What do you think? You have to change x2 or x1? If f of x mid becomes 0, your x mid is a solution itself. We don't need to follow this. I repeat this iteration at all. You have achieved the solution, so you can stop at that point, right? So remember the motto, we need to find the solution. So if f of x mid becomes 0, if it becomes 0, the solution is so simple. But if it most of the times it will be some higher decimal point. So this is general algorithm, but if f of x mid becomes 0, you can just stop the algorithm at once, right? And now, okay, once again, keeping on here, yeah. So see, start is 1, end is 2, 1.50. Yes, this animation, this nomenclature is x1 equal to 2, x2 equal to x1 equal to 1, x2 equal to 2, x mid is 1.5. Just computing, you can see the blue color point is the x mid. This orange color ones are the starting and ending points. So what should I do? It's in the negative part. So I should replace this one with this, right? So I'm just moving this close to this along the curve so that you can understand that we are finding the solution. Now start becomes 1.5, end becomes 2. Now what is the mid value? This 1.75, this orange color. And you can see that it is in the positive direction, positive y-axis direction, which is above x-axis. So what should you do? You should replace this point with this one. So you're moving here to here. Now end becomes 1.75. This midpoint becomes somewhere 1.62. As it is positive again, you are moving it, moving the start to here. It becomes start becomes 1.625, end becomes 1.625, and now the mid becomes somewhere 1.56. So this here, and once again mid becomes somewhere close here. Well, I shouldn't distract. Yeah. So you can see it just moves closer and closer to x-axis, and it eventually end up finding the solution. All right. So I hope you would have understood. Let's play this video once and for all. Just listen it, just watch it carefully how it works. It's so simple, just equivalent to binary search. If you want to know about this further, you can see, look it up for binary search in the algorithm. Oh, you're moving closer and closer to x-axis, replacing whatever the previously existing positive values with the x mid if f of x mid is greater than 0, and the negative y-axis direction in with the x mid if x mid is less than 0, f of x mid is less than 0. Yeah, we ended up with a solution. Solution is somewhere between, see, 1.53, 1.5. It's so close. So which means, this difference is so high. Okay, once again, compute this further and you will end up with somewhere 1.52. No, the motto of numerical methods is not exactly finding the solution. In mathematics, what we have learned, given some formula, we'll exactly find what solution is. But here we are doing it by some repetitive methods. So there you don't need to find what exact solution. We can find somewhere close to. That's what the whole idea behind numerical methods is, because till now we would have been given a formula, you will be substituting values and you will end up getting a correct solution. But numerical methods, we don't have any clue. We don't have any formula at all. We are simply choosing two random points with some, of course, some condition, and then we are just going close. So getting a solution is a prime motto. How accurate it is, it varies with person to person. As you repeat multiple iterations, you will end up with a more accurate solution or something, right? And then now we can infer to bisection method that you can reach the solution after multiple iterations. Let's see. Now analyzing it, we have learned two methods to solve a polynomial. Now let's go back to what our previous discussion was. What mathematicians thought was, whatever they observe, they wanted to write it on paper, right? So they would have found a polynomial, they found a solution for it. Please. Now let's move to differential equation. Why differential equation was needed when polynomial was there? Because we understand that we have been given a polynomial, we know how to solve it. So technically, in a way, we can do whatever we want. Whichever methods, whichever observation we make, we can write it on paper and play with it. Substitute a value, find what would be the result, find some special values, when it will be equal to 0, when will it achieve maxima or something like that, right? Now let's move to something called as differential equations. Why differential equation was needed when polynomial was there? Mathematicians wanted some additional tool. Like polynomial was sufficient, but there were some drawbacks with polynomials, which we will be seeing. Thing is, first let's see something called as different perception about dy by dx. It's like second time coming. What initially we have seen was dy by dx represents the slope of the tangent, right? It represents the slope of a tangent at a point. But in addition to representing it, what it represents is rate of change of one variable with respect to the other variable. Calm down, take a breath, just listen. I'm being given an independent variable. There's a dependent variable which we need to analyze. So it dy by dx what represents is if I change x from this to this to some difference, if I change it by some minute difference, how much y changes? It is a tool, right? Because the whole point of idea is analyzing the things. So if I know how how my dependent variable changes with respect to how I change my independent variable, we can it's like an additional tool given to us, right? So if you didn't understand, wait, let's analyze with further examples. This is an open thing. Once again, I'm saying dy by dx represents rate of change of one variable with respect to another variable, right? So let's say motivation. Let's say when you model something with a definition, two things you need to know. First, you need to know clear function definition. You need to know up to which degree it is there. We can say like laws of motion, if you see, you know that equation h equal to ut plus half at square. We know that up to acceleration we are doing. So only t square term should be there. So we can simply model it. It's so simple. But what if we don't know what it is? What if we don't know what degree it is? So then we can't clearly define the polynomial, right? Because one can define it with degree 100, another can define with degree 5. We can't have any generalization. So that was a key problem. And then you have to, if you know its degree, and it also restricts our knowledge to only polynomials. The functions like sin x, sin inverse x, e power x, log x, these are the important things while modeling systems, right? You will, I mean, modeling systems in the sense, just think of it as you have to represent how population changes, stuff like that. And e power x is what we always use, but polynomials, we can't, the polynomials is completely restricted. Who can say, okay, in Taylor series, we can represent e power x as polynomials, if you say, you know, the degree is indefinite. You will have a constraint on how much you have to do. I can do it till 100, I can do it 200, differs. But we can't even define how e power x is obtained, right? So for that, we can't use polynomials. So that was a key problem. So how dy by dx helps? One of the most important thing people will be using while modeling systems, which I mean, technically they will do is they will change the independent variable. How polynomial works is I will give a value, the function will give me a output value. I don't know how it varies at all, but how dy by dx helps is if I change a value, how does the polynomial change? How does the function change? You know, that serves as an additional tool. In addition to knowing how for the output for the given input, I can change how output varies. The variation is important key term, how output varies with respect to the variation in the input. All right. So this additional tool was always, mathematicians wanted to use this. And most important thing was this differential equation. So let's say how population changes, dp by dt. They have, you can't say at a particular point there are this many people are there. I can model into a polynomial. Like modeling a people population to a polynomial is, I mean, it doesn't make sense, right? It varies with time to time. So that variation, we can model it this derivative dp by dt. How people changes with respect to time. This dt can be anything. It is up to the person who is measuring this. I can take with a day or with 100 years or something. So this dp by dt is nothing but they have taken something like this amount of population into this. This can also be modeled into a polynomial, and which is this. So we are using polynomials. Still, this is a polynomial, but in addition to it, we are reducing it with having an additional tool. We are basically adding a tool called as this derivative. All right. Well, so we can use the derivative to represent the behavior of a function, how it varies. So this was the example which I've started off the session with, bouncing the ball. Now, there we have said y equal to ut plus half at square. Now let's think in this differential equation term. First, let's vary the height with respect to time. They thought, okay, that's a function. Okay, sorry. They found it is a function called velocity. Okay, never mind. This velocity is also a polynomial. Here we are not doing any polynomial. We are just representing with some variables. This is a velocity. This is some function which I don't know. Now, okay, find this velocity is also a dependent variable, right? Varies with time. So what they thought was basically find the variation of v with respect to time. So they are basically finding dy by dt, and they accidentally found it is g, which is a constant. See, the whole equation of h equal to ut plus half at square or y equal to ut plus half at square decomposes to just two equations. Of course, you can say, oh, there are one equation, two equations. It's simple. You are just getting into a simple constant. If it is d is basically a constant, right? So dv by dt or d square y by dt square is v. From this, you can find an equation. I mean, solving it, we don't know. Here, the motivation is how the whole equation of quadratic corresponds to a simple two equation term. That's all, right? So that's all the motivation behind differential equation. Once again, I'm saying polynomial was so helpful. But one thing is we didn't know how much, which degree should we take? What is the highest degree we should use? But this what this derivative gives as the advantage is it helps us to use this variation principle. How, if I change this independent variable from one point to other, how does y changes? And if I keep on doing that, like I can do this to a whole point and I ended up getting a polynomial. I mean, here it can be a polynomial. We can still solve it. But the thing is, we can still end up getting a constant. From basics, we can build up and building a polynomial with definite structure, right? So that's all the motivation behind differential equation. Once again, just first understand why we need differential equation. In addition to polynomial, we are increasing a tool, right? So that's all from my part, I guess. I hope this session was helpful to you. Let me give you a basic summary of what we did here. We just started off with visiting polynomials. That was simple, like telling what dependent variable, independent variable is, and then we ended up in the Newton-Raphson method solving it. Solving was an important point, and for solving it, we had seen there's two methods. Basically, started off with derivatives, and then we did what this iterative methods is, and we started off with Newton-Raphson method definition. We saw some plots, and then we ended up in bisection method. We saw how it works. This basically a binary search thing. If you want to know it, if you want to look it up, you just look it up. And then we saw what is it motivation behind differential equation. This differential equation is what we are going to cover it in next session as well as in other sessions as well. Now I'll hand it over to my friend Madhav, and I think the session was useful. I hope now the second attendance sheet will be released. You can look it up there. Thank you so much. If you have any doubts, you can ask.
The attendance link has been shared. If anyone has any doubts, you can please go ahead and ask right now. The attendance link is out, guys. Please mark your attendance there and we'll continue it after 5 minutes. Meanwhile, if you have any doubts after filling the attendance sheet, you can ask them over here. Yes, so someone raise their hands. You can ask your question. Yeah, go ahead. If you have any questions, you can ask. Is there any reason you raise your hand? Hmm.
Sir, what is the significance of the derivatives? Means if we put the value on differentiating a function, what does it gives?
Yeah, good doubt. Derivative basically gives you an idea about how the function is actually changing with respect to the independent variables. You can have a function changing with multiple independent variables, and it's important to know that how the function is changing with respect to a particular independent variable. So if you want to analyze that, derivatives come into picture. It's not only the
function value that all matters. Like it also the change that matters. In many systems, we need to also describe the system in the future time. So we need the change of the function at a particular time. So there, the derivatives come into picture.
Yes. Priya Gaurav, you can unmute. You can ask your doubt.
Yeah, sure. I had a doubt about the iterations that they spoke about. We know that for a quadratic, we actually know the solution, so we know when to stop. But then when we don't know where the solution stops, how do we get to know the number of iterations we need to do?
Yeah, great doubt actually. We have something called threshold value. So we keep on iterating, and let us say at some point of time we have obtained a xn as some 2.5 or something, 2.5001. In the next iteration, let us say we have obtained 2.50005 or something. If the difference between consecutive values is less than some particular value, so you can say that essentially we have converged to the root. If we notice that the difference is actually increasing, or it is not converting to a particular value, that means that we haven't chosen a good initial point, or it means that the shape of the graph is not so good enough to perform the Newton-Raphson method or the bisection method.
Okay, so the difference is like it's just a guess that we take. It's not predetermined.
Yeah, it's not predetermined. Like we can take the threshold value depending on the precision up to which we want. Let's say you want up to like 3 or 4 significant figures. We can take the threshold value accordingly.
Okay, yeah, thank you.
See, fundamentally, the idea of numerical methods is that you don't get exact solutions, right?
Okay,
So you try more iterations give you better precision, and the amount of precision that you get depends on the number of iterations you make. And the more iterations you make, obviously, has more cost associated with it, but you also get better results. So it's like a trade-off, right? And you choose where to stop. And so
okay,
depending on the shape of the function, you can choose your initial guess and the number of iterations you want to perform to get the required accuracy you desire.
okay. So it's based on us.
Exactly.
Yeah, thank you.
Okay, guys, we'll be starting now. I'll be presenting my screen.
Hello?
Yeah. First, I want to start with well, thank you, Dinabandhan, for that insightful introduction towards differential equation and or some numerical methods to solve polynomials. I think we now have a solid understanding regarding the differential equations, and now we will be going to see what are the methods to solve differential equations and some basic terms regarding differential equations. And at the end, we'll also be looking at the motivation towards numerical methods. Yeah, let us get started. We'll just start with the basic terms of the differential equations. First, I want to mention that you might have encountered these terms earlier. or you might have not. Just no need to worry about anything. Just focus on the session, and it's important to build up upon the basics so that you won't get confused in the further session. Yeah. First, let us start with order of the differential equation. So what the order of a differential equation is? You have a differential equation and you have the derivatives in that equation. So the order of the differential equation is the highest derivative that appears in the equation. Let us see a few examples for this. So we have the first equation. You can see that the derivatives here involved are the second derivative and the first derivative. So the order of the differential equation will be 2 because the second derivative is the highest derivative involved in the differential equation. Next, in the second example, you can see here that the derivative again here involved are second derivative and first derivative. Again, the order of the differential equation is 2. You need to notice something here that it doesn't matter what the exponent of the highest degree is, highest order term is. You can see here that the second derivative has a power of 3, but still the order of the equation is 2. You just need not care about the exponent. It's just the highest derivative that matters. And also I want to mention that why there is a need of the term order of the differential equation. Order of a differential equation helps to understand the complexity of the system that we are looking at and what we want to analyze. So the higher the order, that means the more intricate dynamic behavior the system has. For example, you might have come across the oscillation and the SHM equation, the second order differential equation. It means that the oscillations are involved in the system. What if we have the higher order derivative, like fourth derivative or third derivative? In those systems, many terms come into play, like resonance, higher modes of oscillation. If you aren't familiar with these terms, it's okay. But it's important to know that the higher the order is, the more complex the system is. And we also need to note that the order also explains you the number of constants involved in the solution of the differential equation. You can see that the order of the differential equation here is 2. That means for the solution of y of x, it's important to note that the solution y of x is actually a family of curves. It's not just a single function that satisfies the differential equation. We have multiple constants involved in the solution as well. So that means we have 2 constants in the solution for the differential equation. And depending upon the initial conditions, we obtain those constants. Someone has unmuted the mic, I guess. Can you mute that? Yeah, thank you. We'll continue with the degree of the differential equation. Simply put, the degree of a differential equation is the exponent of the highest derivative of that appears in the equation. And there are some conditions that are met to be satisfied for the degree. The first condition is the differential equation must be free of any fractional or negative powers. That means the differential equation must be written in form of a polynomial. You have come across polynomials, right? X cube plus x square plus x plus 1, something like that. If you imagine y triple dash as x cube and y double dash as x square and y dash as x, you should notice that the function should be in terms of a polynomial. And one more important criteria is transcendental function like trigonometric, sin x, cos x, exponential, e power x, ln x. Those functions should not act on the derivatives. That is another important criteria that need to be satisfied. Let us see some examples before moving forward. We have the first example. Here you can see that the highest derivative involved is cubic. So here it is y cube, something like that. D cube by dx cube. And the exponent of that is 2. So the degree of is 2. But notice that the order of the differential equation still remains as 3. Because the highest order involved is 3. Sorry. Yeah. In the second example, notice that the sine function is acting on the second derivative, d2y by dx square. We have the criteria that the transcendental function should not be involved on the derivatives. So here the sin x is acting on the second derivative. So we conclude that the degree is not defined here. And I want to mention here that the definition of degree is not complete, in the sense that we can always raise the equation to some power. For example, consider the differential equation y dash equal to x. That means dy by dx equal to x. We can always cube this differential equation to obtain y double dash whole cube equal to x cube. You can argue that the degree is 3 here. This is the drawback of the degree definition of degree. Most of the modern textbooks doesn't even define degree, but still we use the term degree because it helps us classifying the differential equation, and it also helps to understand the nature of solutions as well. With degree, we can it is more useful in terms of linear differential equation, which we will see in some time. Yeah. If you have any doubts regarding order and degree, feel free to ask in chat box. I will be looking at that as well. We will go with a question before moving forward. Chat mods, I request you to please put on a poll in the chat box. We have a differential equation here, and I want you to find out the order and degree of this equation. We have pretty good responses. That's nice, guys. Keep the M2 up for the whole session. I see Vasudev, Krishna, and Rohit Kumar again answered the question first. Yeah. Let us discuss the answer for this. Yeah. Here you can see that first you need to notice that there's a power of 3 by 4, which is not a natural number. You can see that this is not in the polynomial form. So one thing we have to do is we need to raise the equation to the 4th power on both sides. If you raise it to the 4th power, you can see that the highest derivative involved is 7 here. So we need not focus about the right hand side of the differential equation. We just need to focus on the left hand side. We have the highest order as 7 and the power of that to be 3. So from the definition, we have the order as 7 and the degree as 3. Pretty simple, right? Yeah. We'll continue now. Till now, we have discussed some terms like order and degree. Now we are going to look at classification of differential equations. So why do we need classification of differential equations? See, for solving any type of differential equation, it's important to find what type of differential equation it is. It helps us give some insights about the solutions, and it helps us to choose the method correctly. Just as a doctor need to diagnose why before treating an illness, we need to find what type of differential equation before just blindly trying to solve the differential equation analytically. This classification also helps us to choose appropriate methods numerically to solve the differential equation, which we will see in some future time. We have the first classification, ordinary and partial differential equations. The ordinary differential equations are the differential equations which involves only exactly one derivative with exactly one single independent variable. I repeat, the ordinary differential equations are the differential equations which involves derivatives with respect to only one single independent variable. That means this might sound too technical for you. Let me put it this way. So imagine you are driving a car and you want to model the system that it is. So we have the acceleration of the car and the velocity of the car. So the independent variable here involved is either displacement or time, because those two are involved. So we can model the differential equation to be in the form of displacement and time, or velocity and displacement, either of those. And on the contrast, we have partial differential equations, which have derivatives with respect to multiple independent variables. This means that these are useful to describe the systems which varies with respect to multiple independent variables. For example, imagine the room I'm sitting in. Here the temperature is pretty high actually. The temperature varies with respect to spatial coordinates x, y, z, and also with respect to time. So to model the system, that is the room, and to find out the temperature with respect to time or the spatial coordinates, we have the x, y, z, and time. So this is a differential equation which has multiple independent variables like x, y, z, and time. We'll see some examples before moving forward. We have in ordinary differential equations the radioactive decay, which helps us to find the age of fossils, etc. You should have often come across this equation if you're into JE, and don't get intimidated if you haven't seen these equations before, or by seeing these operators and all. These are just to give an idea about what ordinary differential equations and or why partial differential equations are. We have the SHM equation. This is quite famous actually. Here you can see that the only derivative involved is with respect to time. And we have the Newton's laws of cooling explaining why the coffee that you are drinking right now cools down with respect to time after some time. And we have the wave equation, which explains why you are able to hear me when I speak. And we have the Schrodinger equation, which almost describes every quantum phenomena. And we have Maxwell's equation, which explains why the communication in present day is possible. You need not worry about these operators. These are called Laplacian operators. If you are interested in vector calculus, you can just try Google them or see some videos in YouTube. The next classification we have is linear differential equations. Again, this is an important fundamental differential equation type we are going to look at. So what is a linear differential equation? The linear differential equation is modeled by a polynomial with respect to y, and you have the coefficients as a function of x. You see here that we have y, y dash, y double dash, yn, and b of x. Just like a polynomial, right? We have let's say y power 5, y power 4, y cube, y square, y, and so on. We have some examples also here. The first is linear first order differential equation. We have this. You can see that we have y dash involved and y involved. And in the second example, you can see that all the coefficients are with respect to x are constant. And you can see that we have y double dash term, y dash term, and y term. Yeah, let us go forward. Before going to the homogeneous differential equation, I want to mention why linear differential equation classification is important. See, linear differential equations are those type of differential equation that almost comes into picture everywhere. You either take the electrical circuits or signal processing everywhere. You can see them almost everywhere, and it's important to understand how to solve them analytically as well as numerically. So we need the term linear differential equation. We next have homogeneous differential equation. The definition is a bit involved, so I will simplify it for you. We have a differential equation which can be represented as a function f of x, y, y dash, and so on as 0. For example, you can in this example you can take the sin x to the left hand side and say that the entire left hand side is a function of the terms y double dash, y dash, and y and x. Having modeled a differential equation like that, it is said to be homogeneous if it is invariant. That means the differential equation essentially remains same. you can observe that by changing the variables x to x prime, that is a power k into x, and y prime to a power l into y. Here a is a parameter and k and l are some real numbers. So after applying the transformation, we get that this differential equation f of x prime, y prime, and so on equal to 0, which is essentially same as the first differential equation. So we can see that here the linear homogeneous ordinary differential equation is of the form as shown. Here you can see that what transformation can you think of to apply so that you can say it as homogeneous. Think about it. One clue is you have all the functions of x, an of x, an minus 1 of x, a1 of x, and a naught of x. So you don't know what those functions are. These could be polynomial, or those could be transcendental, or something, some random functions. So you can't apply a transformation to x. So that makes us essentially to choose k as 0. That means we are not changing the variable x, and we are changing the variable y. Let's say y prime is some a times y. If we replace the y with y prime by a, we can see that the a comes out outside, and we can essentially multiply by a to keep the differential equation same. That means the differential equation is same as the older differential equation. There are also multiple classifications among homogeneous equations as well. We define homogeneous differential equation just to make sure that it is easy to solve the differential equation. We have multiple ways to solve homogeneous equations. It's actually pretty involved, and if you are so much interested about it, you can check out some books for that. It's actually quite interesting. Let us see some examples about these classifications also. We have the linear homogeneous, linear non-homogeneous, all the 4 combinations. It's important to note that there's no such, if something is linear, it can be non-homogeneous or homogeneous. Those two are completely independent terms, and a linear an equation can be either linear or non-linear, and homogeneous or non-homogeneous. You can look at these examples later also, and we also have a question on this in the assignment also. Please look at it. Up to now, we have seen some basic terminology of differential equation and understood some classifications of the differential equations. Now it's important to know how to solve the differential equations analytically. By analytically, I mean by pen and paper. Like by you get a exact answer for those differential equations. Later, we will also see some numerical methods for solving differential equations in further sessions. So what solving the differential equations means? Solving essentially means you need to find the set of functions that satisfy the differential equation. By set of functions, I mean that a family of functions satisfies the differential equation. The function may be either implicit or explicit. You just need to obtain a mathematical expression for the function. We have these classical methods of solving differential equations. We have variable separable, which I think most of you have known or heard about it. It's okay if you don't. And we have exact differentials. We have integrating factor also. So these two types are actually related. So make sure that you listen to exact differential carefully before moving to integrating factor, because we use that technique in integrating factor. We have the first type, variable separable, which is a most fundamental and easiest form of solving differential equations. In variable separable, we have the differential. It's actually a first order differential equation. We have y dash equal to p of x into q of phi. Notice that the functions with respect to x and y are completely separated. So this is the clue to apply variable separable. We have dy by dx into 1 by qy is p of x. You can just basically integrate on both sides to obtain the function. Let us see some example. I think you must be pretty comfortable with integration by now. If not, let us know in the chat box. We have the initial
So first, I need to explain what the initial value problem is. Initial value problem is just an ordinary differential equation with the initial conditions mentioned. So let us think you want to model the trajectory. So you need to have the initial conditions, like the initial velocity or the initial position, to find out the solution completely. That is called initial value problem. Here we have the initial condition y of pi by 2 equal to 3, and we have an ordinary differential equation as well. So try this. I'll give you a couple of minutes to try this, and I'll explain the solution. Meanwhile, if you have any doubts, feel free to answer this. I'll Okay. I think you should have been done by now. We'll look at the solution. We have this differential equation 1 plus e power y into y dash equal to cos x. We can just take the dx here and integrate on both sides. Oh, sorry guys, there's a small typo here. It should be y here. We have y plus e power y equal the integration of cos x being sin x, and we have a constant. We can obtain this constant by the initial condition given y of pi by 2 equal to 3. Sorry for the typo. Here there should be a y, and you obtain c as e cube. So the function equation is like y plus e power y equal to sin x plus e cube. I mention again, here there should be a y. It's just a typo. Sorry again. Yeah. We next have exact differentials. You might not have seen this before. It's another interesting type of differential equations. We have some involved methods to solve them. So let us go into it. If you have any doubts regarding the variable separable or the example, feel free to ask in the chat box. We have the first order differential equation of the form m of xy dx plus n of xy into dy equal to 0. So the motivation behind exact differential equations is, so like you might have come across electric fields and potentials, right? Uh, you know that this can be, so let us see what exactly it is first, and then going to electric fields and potentials. First, m dx plus n dy, I want to write it as d of some function. If I'm able to write this equation as d of some function, we are essentially done with the equation. We have d of something equal to 0. That essentially means phi equal to c. So just need to find the function phi satisfying this. But it is not always possible to find a function like that. There are differential equations which satisfy that and which don't satisfy this. The ones which satisfy this are called exact differential equations. So if we differentiate this, and we have the chain rule, dou phi by dou x into dx plus dou phi by dou y into dy. If you are not sure about what chain rule is, let me put it in a simple way. We have the function phi of xy. We need to find out the change in the function phi of xy with respect to some variable or something. I need to find a small change in phi of xy with respect to small change in x and y. So what I can essentially do is, in the graph, I can move a small amount of small amount in direction of x, and then I can move a small amount in the direction of phi. We have partial derivatives involved here because I'm essentially keeping y constant while moving in the direction of x and keeping x constant while moving in the direction of y. So we have dou phi by dou x into dx plus dou phi by dou y into dy equal to m dx plus n dy. By comparing the terms, we can see that dou phi by dou x is m and dou phi by dou y is n. These are essentially like two linear equations or something like that. You have let us say we have two linear equations with just one variable. We have the variable as phi here. We know already the functions m and n. So we have two equations with one variable. Do you think always a solution exists for that? No. This is an overdetermined system. Namely, we have two equations with one unknown function, that is phi. So if you want to get a solution for phi, we need to ensure that there's a particular condition in multivariable calculus which states that if you have a double differentiable function f fxy equal to f x. That means if you differentiate f with respect to x and then y, or the other way around with respect to y and then x, those essentially gives the same answer. Quite interesting, right? We'll apply this here. Since we know that phi is continuous and differentiable, we can differentiate with respect to y on both sides. We have dou by dou y of m is equal to phi by x, and dou by dou x of n is equal to phi x y. Since those two are equal, we have dou m by dou y equal to dou n by dou x. So this is an essential necessary condition to satisfy to say that a differential equation is an exact differential equation. If we know that this condition is satisfied, we are sure that we are going to find a solution for phi. We'll see how you are going to find a solution for phi in the next slide. We take the first equation, dou phi by dou x is m. If we just integrate with respect to x on both sides, we have phi equal to integral of x, integral of m plus g of phi. We have a g of phi just because here we have the differential with respect to x. That means y is constant. Hence, if we differentiate this equation with x, the g of phi term essentially vanishes. So we can still add a function g of phi to ensure that the second equation is also satisfied. If there were no g of phi, we can just obtain phi's integral m and just ignore the second equation. But it's not like that. We have the second equation as well, and also we have a arbitrary function g of phi. That makes sense, right? Sorry. So let us substitute the obtained equation in the second equation. We will get dou phi by, we'll obtain dou phi by dou y as dou by dou y of integral m plus dou by dou y of g of phi. We substitute that here, we get this equation. Dou by dou y of g of phi equal to n minus dou by dou y of integral m. We can just essentially integrate the function m first and then differentiate with respect to y, and then obtain a function here on the right hand side. And then we have just a first order differential equation, which is pretty straightforward to solve. And we can find g of phi by that method. Having found g of phi, we can just substitute here to find phi. And having found phi from the previous definition, we can see that d of phi is essentially 0. That gives us the solution, phi is c. So before moving forward, we will take the attendance now. I think chat mods will put the attendance form right now, and also try this solution before, if you are done with giving the attendance. Meanwhile, if you have any doubts, I can answer them in the chat box. Guys, keep in mind that we will be having
10 attendance forms throughout this summer school in all 3 sessions. It's mandatory that you need to give attendance in at least 8 of them to get the certificate. We have 3 in this session, and the remaining 7 will be there in the next 2 sessions.
Madhav, can you explain exact differentials again? Someone's asking.
Okay, yeah. I'll give you a brief idea of what I have explained right now. See, you have a differential equation of the form mdx plus ndy equal to 0. And your intention is to find the solution in the most easiest way possible. So what if you are able to write this differential on the left hand side in this form? If you are able to write this in the form of d of some function is equal to 0, we are essentially done, right? We just have phi is c. So that is the motivation behind exact differentials. Think it of in this way. You should have come across electric fields and potentials, right? See, we have the gradient of potential to be 0. Gradient of potential to be the electric field. The phi here is similar to the gradient. We have gradient of potential. Sorry, we can take the phi to be a potential and just take the gradient to give this one. Dou phi by dou x into dx plus dou phi by dou y into dy. If you want to, if you are able to find a potential like that, then we are done, right? We have this. Let us take this as electric field vector. We have m as x component of electric field and n as y component of electric field. If you are able to write electric field as gradient of the potential phi, let us think phi as potential. If you are able to write this phi, the gradient of phi, which is essentially is dou phi by dou x into dx plus dou phi by dou y into dy. If you are able to find a function phi, then we are done, right? So that is the complete motivation behind exact differentials. And to obtain a gradient for to obtain a potential for electric field, the condition that electric field must satisfy is the electric field should be conservative. And for conservative, we have the condition the y derivative of the x component of electric field is equal to x derivative of y component of electric field. This is the condition we obtain here. So if this condition is satisfied, that means we are able to model the left hand side as d of some function phi. Having found phi, we can just that means the differential equation is solved. So we have these two equations, dou phi by dou x equal to m and dou phi by dou y equal to n. If you are able to solve these equations and find a particular function phi, then we are done. To find phi, we just need to integrate these equations and put them in the other equation. Just because here there are partial derivatives involved and the constants here will be functions of y. If we integrating by x, the function will be a function of y. If you're integrating by y, the constant function will be a function of x. Just like in indefinite calculus, here we have the constant as constant function. Here we have phi is equal to integral of m plus g of phi. And we can just put it in the second equation. It's just like solving an initial value problem. And it's just that we have one equation and the boundary condition is the second equation. You can just think it of like that. And you can just plug it into the second equation and obtain g here. When we obtain g, we can just substitute back into the first equation to obtain the function phi. I guess in a nutshell, differential equations are just like solving two differential equations and just obtain a function which satisfy d of phi equal to 0. Yeah. If you have any more doubts, feel free to ask in the chat box. Yeah. Someone asked, Nagakirtana, someone asked why the condition should be followed. It's something called Clairaut's theorem in multivariable calculus. We are not going into the proof of that right now. You can always look to it in some textbooks or in Google. Yeah, I'll just show you the question. I guess you should be done by now. So I'll just walk through the solution. Sorry. Yeah, we have the differential equation of the form m dx plus n dy equal to 0. If you just take multiply by dx on both sides, you will get into this form. By comparing, you have m is 3y plus e power x and n as 3x plus cos y. The first thing you can notice here that the y derivative of this is 3 and the x derivative of this is also 3. You can see that these two are equal. Hence, you can say that this is an exact differential equation. This is the crucial part in solving exact differential equation. It's important to identify first that this is an exact differential equation. Most of the people fail in identifying the differential equation as exact differential and just try solving this in some random ways. But if we identify this as an exact differential equation, we just can solve in a simple way. We have these differential equations. Dou phi by dou x is m. That is 3y plus e power x. And if we integrate this on both sides with respect to x, notice that y is constant here. So if we integrate with respect to x, we have 3xy plus e power x plus g of phi. Because we are integrating with respect to x, we have a constant function g of phi. And again, from the previous slide, we had dou phi by dou y as n. So if we just differentiate with respect to y, we have 3x plus. Since we are differentiating with respect to y, the e power x vanishes, and we have g dash of y equal to n, and then is essentially 3x plus cos y. So we essentially have g dash of y equal to cos phi, which is just a basic variable separable equation. You can see that everything is interrelated, right? We have g of y is sin y. We are just not considering the constant here because we already have a constant in the final solution. Adding constants or multiplying constant essentially just gives a constant, right? Yeah. We have the solution 3x plus e power x plus sin y equal to c. Notice that this is a family of curves, and if you map them on the graph, it will be so beautiful to see them. Yeah. So up to now, we have seen what exact differential equations are, and we have solved the problem also. So you might have a question. What if the differential equation given is not in the form as mentioned before? So if the function is not in the form as mentioned, you can just multiply some factor called integrating factor on the both sides to keep the differential equation essentially same and making it an exact differential. That is the motive behind integrating factor. We have the general form mxy dx plus nxy dy equal to 0. We can also solve this by integrating factors, having satisfied some specific conditions, but we are not going too deep into the integrating factors. You can always look into some textbooks or Google them. We are not going too deep into them. We are just seeing the basic version of the linear non-homogeneous equation. We have the linear non-homogeneous equation y dash plus p of x into y equal to q of x. This is the most famous equation, or the like you should have come across this many times. Integrating factor in chemical kinetics, in math, everywhere. You should have seen this many times. But we'll see the math behind it now. We have dy plus p of xy dx equal to p of x dx. We need to see that this may not be always an exact differential. That is, the condition mentioned before may not always be satisfied. So we need to make this as an exact differential by multiplying with suitable factor called the integrating factor. Let it be g of x. So if you multiply this by g of x and convert it into this form, we have g of x dy plus y p of x minus q of x into g of x dx equal to 0.
I'll give you some time to just check what we have done till now. We have a differential equation, and we know that it is not an exact differential equation. We first check whether the exact differential criteria is satisfied or not, and then we know that this is not an exact differential, but still we want to solve that differential equation. One trick kind of thing we can do is we can multiply the whole equation with some factor to essentially keep the differential equation same, and then make it as an exact differential. Now we need to make this as an exact differential. We know that the x derivative of m function should be equal to the y derivative of the n function to make it as an exact differential. I repeat, we need to ensure that the x derivative of n function, sorry, I repeat, the x derivative of n function should be same as the y derivative of the m function. It's just reverse. So the x derivative of g of x is equal to the y derivative of this function. So since this is a pure function of x, we can just cancel this because it essentially vanishes, and we can obtain g dash of x equal to p of x g of x, because p of x and g of x are pure functions of x and we are differentiating with respect to y. So now we have obtained a variable separable equation. Essentially we have g, wait, yeah, this is a variable separable equation. We can just separate out the terms and just integrate on both sides to obtain g. Just no need to put a pen on the paper to solve this. It's quite simple. It's dg by g is equal to p of x into dx. We just integrate on both sides. We will obtain g is equal to e power integral p of x dx. Here we didn't take any constant because, however, we are going to include it in the final answer. So we have obtained g of x now. Now what you can do is you can just multiply the whole equation by g of x. And now that we are after multiplying with g of x, this is an exact differential. We can again apply the previous technique of exact differential to solve the obtained differential equation. In a nutshell, we just find the integrating factor and just multiplying it on the both sides will give this equation. And just we can integrate on the both sides to obtain the function y. Yeah, we have an example here. You can just solve this. I will give you a couple of minutes to solve this and put the answer in the chat box. In the meantime, I'll look at some doubts. Yeah, I can see that many of you answer this chat box. Trucker, you got it right, I guess. Well, let's walk through to the solution. See, we have the integrating factor as e power p of x into dx. That is, the p is essentially 3 by x. So we have e power 3 by x dx. This is just a normal integral. 3 by x dx integral is just 3 ln x. We just substitute it here. We have e power ln x cube, which is essentially x cube. So now we have found out that the integrating factor is x cube. Now we need to multiply the whole equation with x cube and make it as an exact differential. So if you multiply with the x cube on both sides, you have x cube dy by dx plus 3x square y equal to e power x. Now this is an exact differential. I also want to mention that sometimes it's obvious to see that this is the differential of some function. Here it is x cube y. Here it is like d of x cube into y. You can sometimes look it by eyes. Like, just no need to go step by step by using the technique of exact differentials again. We have x cubed by d of x cubed by equal to e power x. If we integrate it on both sides, we obtain x cubed by equal to e power x plus c. This is not only the case with integrating factors, but also the exact differentials also. Sometimes we can just see it and say this is differential of some function and just integrate on both sides to obtain that function. Yeah. Yeah. Up to now, you have seen some basic terms of differential equation, classification of differential equation, and some classical methods to solve the differential equations. Now it's time to discuss why. Now it's time to see beyond equations. We have been doing math till now by using equations and all. Now it's time to see why analytical solutions fall short. So first I want to discuss what are analytical solutions. Analytical solutions are closed form expressions which essentially involves math expression and are solved like analytically or by hand. These are the methods up to now you have seen, like the exact differentials or the integrating factors. We have some other methods also. We are not going into them now. So these solutions are exact and often easier to interpret. Since we have obtained the solution in the closed form, we can just plot it or do some analysis of those functions to analyze the system given. But we need to keep in mind that if we dive deep into the differentials equations and real life phenomena, we are not sure we're always going to run up to simple equations and equations that are obvious to solve, like integrating factor equations or the exact differentials and so on. We often come across very complex differential equations and which are impossible to solve by hand at all. In this time, analytical solutions are not important. We have some other methods to solve the differential equation, analyze the system properly. I want to mention that many times we often rely on some assumptions and simplifications that are imposed on the system to make the differential equation simple. But that is not always the case with real life scenarios. I'll give you an example for this. Before giving an example, I want to also why the analytical solutions are not always useful. As I mentioned, many real world problems lead to differential equations that are highly complex and non-linear. It's not possible to solve like let's say you have 1,000 system of differential equations and you need to solve them by hand. It's not feasible to solve them by hand. So mathematicians have thought about it and devise some ways to solve the differential equations and many not only differential equations but many problems that are difficult to solve by hand. And yeah, the example I was mentioning about was Navier-Stokes equations. You might have come across this before in the JEE also. The Navier-Stokes equation essentially model the flow of a fluid, whether it may be a air or maybe a lake. So imagine you want to model the flow of monsoons, or you want to predict the weather. You use Navier-Stokes equations and model them. But what if you are required to solve them in the real life situations with air drag and like many other phenomena happening in everyday life? It's not completely possible to include all the terms into this equation to solve this analytically. We have the friction here, we have external forces, we have pressure gradient and so on. So it's not possible to completely solve the system by hand. Hence we apply some hence we apply some simplifications or assumptions on the system to make the differential equation simple and analytically feasible to solve. But that's not always the case, right? If you want to completely predict the system accurately, let's say we want to predict the arrival of monsoon at a particular place, we just can't ignore the some other phenomena happening and just try to make the differential equation simple enough. We just need to include every possible phenomena into the differential equations and just solve them. But for this, analytical equations are not completely feasible. We need to find some other ways to solve these differential equations. For example, you might have applied some constraints on the system like streamlined flow or like uncompressible fluid or say what no slip condition and so on. These are the conditions just to make the differential equation simple to solve, but we can't rely on that always. I just mentioned them about them here. We also have boundary conditions to be satisfied. What are boundary conditions? Boundary conditions are the conditions that are required for the system to satisfy at the boundaries. Like for example, the pressure and the velocity gradients at the boundaries of the fluid domain. Analytical solutions might require simplifications or assumptions that do not hold for all conditions. As I mentioned before, analytical solutions require some simplifications to solve them exactly by hand. So given these limitations, alternate methods are often used. Those are numerical methods and qualitative methods. So I'll give a brief introduction about what numerical methods are, and I'll also give some examples of what numerical methods are. You already seen in the session given by Dinabandhan some polynomial root finding techniques, which are like used by computers to find the root of the polynomial exact enough. Yeah. So we'll see what numerical analysis is first. Now, up to this point, your experience with math is that you are given a problem and you want to find an exact solution for that. You try to approach that by a sequence of steps following from question to answer. But math is not entirely that. So imagine we want to find some, let us say, let me give an example. Like, imagine you want to solve a system of 1,000 linear equations. You can't keep solving them by hand and obtain a obtain the solutions after some 100 days or something like that. As we delve deeper into the differential equations, more complex systems keep arising, and it's not possible to solve them completely by hand. And so we have divided some methods to solve them by computers and algorithms. So yeah, what is numerical analysis? Is numerical analysis is generally iterative in nature. For example, it's appropriate in numerical analysis to repeatedly guess the solution until you obtain a solution that is quite close to actual solution. This idea is maybe we don't need an exact solution for the question. We just need an answer which is quite close enough to the exact solution. And this might seem quite weird for you, but this is what most engineers tend to do, and this is what engineers tend to have different mindset with compared to mathematicians. We try to end with the answer that is as close as possible, and for that to possible, we divide some algorithms or ways to do that. So since we have a design to solve the system and find the solution which is quite close enough to actual solution, we can always account for the possible errors, and we can always change the design to ensure that we minimize those errors and make the answer close to actual or analytical answer. We'll see why numerical methods are employed. The first reason why is to solve mathematical problem that cannot be solved exactly. I'll give you an example for this. What you see now is a normal curve. You have this integral, and imagine if you want to find the area under this curve. It is essentially the integral minus infinity to infinity, minus infinity to x, e power minus u square by 2 du. I want to mention that this integral is possible to solve by hand only if x is infinity. For the remaining terms, or 0 at least, like, yeah, if x is 0 or infinity, we can obtain the exact solution by hand. But what if x is some other answer and we need to find the area under this graph?
So we then need to find some other way to do that. One possible solution could be, first we need to think what area is. We can break down this area of region into small triangles or strips, and then we can add them to obtain the area. We have some other methods also called Simpson's method and Simpson's 1/3 rule, 3/8 rule. We'll just discuss about them in the future sessions. And the other reason why we need numerical methods is to solve a problem that is intractable. As I mentioned before, imagine you need to solve a large set of equations like this. You can't keep solving them by hand, right? You need some methods to solve them. And let us think you have found some way to solve them numerically. But is it feasible to solve by hand again obtain numerically? Think of it. Like as previously discussed, we had Newton-Raphson method. We have some iterative methods to do that. Let's say xn plus 1 equal to 2 plus xn, or root of 2 plus xn. We just can't substitute, keep on go substitute xn equal to 1 and then further substitutions like 100 times or 200 times or 1000 times to obtain the converging value, right? We need some computational methods to do that. This is solved by the help of computers or algorithms. We just make an algorithm and give it to a computer to solve that by itself. So example of that kind of algorithm is one is gradient descent. As mentioned earlier by Dinabandhan, this is quite similar to Newton-Raphson, but the aim here is not to find the root, but we need to find the minimum value of a function. We need to optimize a function. Let us say, like recently the elections has concluded. Before the elections, like let us say Modi wants to visit the entire country, like not entire country, like maybe some places, and he want to campaign. This is called as traveling salesman's problem in machine learning. So what if he wants to find a shortest path to solve to go through all the cities and return to the initial point? You can just keep track of all the distances and add them manually and find the shortest route. There may be a much shorter route than that. So we use gradient descent there to optimize the shortest distance of the path. So what the gradient descent essentially do is you start off from a particular point and you go in the direction in which the change is maximum or minimum actually. The direction in which the change is maximum is given by the gradient of a function. I'm just giving brief idea of that. You can always look into the video of three blue one brown, which is actually quite formidable. Like you can just go through that. He explained it so interestingly. I'll just give you a brief idea of that. You go in the direction of the minimum change. The maximum change direction is given by the gradient. So the negative direction of gradient is what the change in minimum. You can just keep going in that direction and to obtain the final answer. So up to now, we have discussed why numerical methods are important to find solutions for where the real life scenarios where the analytical solutions fall short. So for doing that, we need algorithms. But after finding algorithm also, but how to solve them? How to solve the algorithm? Like let us say you are given a problem and you are given an algorithm. You need to find the final answer. It's not possible for you to compute entire by hand. So for doing that, we use the computational power of computers. Whether it may be a laptop that you are viewing right now, or it may be a cool supercomputer in IIT Madras. It all depends on computational strength of the system, how fast we are going to do it. But how are we going to do that? We have high-level programming language. Apart from, you might know some tools for scientific computing like NumPy or something like that in Python. Apart from that, we also have high-level programming language written especially from numerical computations. These are MathLab, Octave, Mathematica. There are others also, but these are the most prominent ones. MathLab is an excellent software, but this is a paid. Like this is paid. We don't you need a license for this to do it. And Octave is entirely free and open source also. So we will be using Octave for the next 2 sessions to solve the algorithms. Yeah. So go ahead and start installing Octave in your device and try to play with it. We will also guide you regarding that in the WhatsApp groups, and we will also post some links in the channel also. Here I have attached a link here in the slide too. You can just watch it and follow the procedure to install the Octave on your device, and just try to play with it and try to run some simple calculations like addition, subtraction, etc. You can also refer to the documentation if you are interested. So that's all for now. If you have any doubts, we'll be glad to take that. We'll be posting all the relevant links and assignment also in the WhatsApp and channel too. If you have any doubts, you can just ask them. You can also raise your hand. I can unmute you. Yeah. Rajarshi Chakraborty. Yeah. You can speak now. And Nitish too.
Hello.
Yeah.
Can we get the PPT file of this session?
Yeah, sure. We'll send all the links in the WhatsApp and also the Teams.
Okay, thank you.
Stay tuned. Yeah.
So we will be sending a problem set after this session. So you can go through the instructions. We'll be sending it on WhatsApp. All of you can go through the problem set, and you should solve the problem set before the deadline mentioned in the sheet.
How should we submit the answers to the problem set? Yeah. You can just write them. As long they are clean and legible, will be accepted.
Where do we submit them though after scanning the sheet?
We will share a form where you can submit. All the instructions will be sent on WhatsApp. Don't worry. All the necessary information will be sent on WhatsApp.
Okay, thank you.
All right.
And note that you need to submit all the 3 assignments for the upcoming sessions also. We'll also wait, nothing. Yeah.
Yes, you will be the concept that you learn in this program will also help you in machine learning if you're planning to do that. Madhav, I'll take over. So hello everyone. I just wanted officially the session is over. Just wanted to highlight the fact that the Mathematics Club has we have released our website recently, and we'd appreciate it if all of you took a look at it. We'll send the link for the website in the WhatsApp group. So this is our website. It basically contains all our events, who we are, our vision, and some of the things that we have done over the past and what we're planning to do in the future. So one of the important things that we're planning to do in the future that might interest all of you is our mathematical competition, which we're we're planning to conduct in the future. So it's called Srinivasa Ramanujan Mathematics Competition. So it's available on the website. You can read through the details of the competition, but it's open to all colleges and high school students. And we have cash prizes up to around or more than 10,000 rupees. So it's a great opportunity for all of you to again come back and participate in another IIT Madras organized event. So just take a look at this, and we have a registration. You can join this WhatsApp group available, whose link is available on the website to keep updated with regards to the maths competition. In addition to that, we'll also be regularly engaging with all of you through our various social media handles like our Instagram, our YouTube, LinkedIn, and you can always contact us through mail as well. So do follow us on LinkedIn, YouTube, and Instagram. We'll have regular fun problems, questions, discussions, and yes, you can always feel free to contact us and ask us about any other ideas or collaboration that you might have. So just putting that out there. So do look at our website. We will be sharing. You can even find details about the summer school here, but so you can find out about projects or events, about our club, all the members in our club, and more like our contingent and so on. So that's all for now. That's all for this session. Thank you very much for attending. We do apologize for the for the inconvenience caused due to the teams. Well, hopefully, most of your issues have been sorted by now. If some of your issues have not yet been sorted, we will, don't worry, we'll look into them right now and we'll sort them out by the end of today. You can always contact us. The group admins are there in the WhatsApp group. I am Atreya, one of the heads of the Mathematics Club. So you can contact either us or the coordinators, all of whom are admins, and we'll be very happy to assist you with any questions about either summer school or any other events of the Mathematics Club. So thank you all for attending and see you next time. Yes. Also, please fill the feedback form. We've shared it here. We'll also share it on the WhatsApp group. So we'd really appreciate any feedback that you give us. We'll try to incorporate all the necessary changes in the next meeting, next session.